This simulation looks at the behavior during temperature program desorption. And this snapshot shows we're plotting the rate of desorption as a function of temperature, where we're heating up a surface that has molecules adsorbed on it. There's no reaction, we're just looking at how they desorb. And beta corresponds to how fast we heat it. So it's a linear temperature rise. It can be 1, 3, or 10 degrees Kelvin per second. And so the rate's going to depend on how fast we heat it. And the temperature where it goes through a maximum also depends on how fast we heat it. So in this simulation, we're looking at first order desorption. We can change the activation energy, and that's going to change the location where we go through a maximum. We can change the coverage, and that's going to change the amplitude. And also, for example, for second order, changing the coverage will change the maximum temperature. So the idea is this is a technique that's used extensively in characterizing catalysts and studying adsorption behavior, and it helps to understand the kind of information we can get out of it. The other way we can plot this, if we select time, is we plot rate versus time, and the behavior then is different, because when we heat at a very fast rate, the green line, this occurs over a relatively short time. The slow rate, blue, is over a longer time. On a rate versus time plot, then the areas would be the same, because the areas are proportional how much material desorbs. And basically we're raising temperature high enough until desorption rate goes to zero. Everything that was adsorbed on the surface has desorbed. So now we'll look at the interactive simulation to better understand this behavior. So here's the interactive simulation, and we're plotting for first order rate versus temperature. If we plot instead versus time, notice how spread out they are in time, because the one that we heat at the slow rate, 1 degree per second, the blue line, takes much longer to get to complete desorption. And though it may not be obvious, the area under each of these curves is the same. The area is proportional to the amount. As we change the activation energy, then we shift these to higher temperatures for higher activation energy. On a temperature plot, we can see the behavior. If we change the coverage, then what we're changing is the scale here. In first order, it's not a significant difference. They just look bigger. But for zero order, as we change the coverage, then the peaks actually move to higher temperature. Second order, it's the reverse. Notice the behavior for zero order. Zero order means it just desorbs at a constant rate till everything's gone. The rate drops to zero. Again, on a plot, they're spread out in time. So temperature program desorption, it's important to understand particularly the effect of heating rate, because, for example, the change in this peak temperature with heating rate is often used to back out what the activation energy is for desorption.